Good morning, everybody. So we're going to get started now. Welcome to another one of the LIGO Virgo Cagra webinar series. This morning, you're going to hear a presentation about listening for signals from the distant universe. And I'm going to hand you over to Andrew Mattis, who's going to moderate this webinar today. Andrew.
All right, thank you, Patrick. So thank you all for logging in this morning. We're going to present work from two recent papers by the LIGO Scientific Collaboration, Virgo Collaboration, and Cagra Collaboration. The first one presents results for a search for an isotropic gravitational wave background using data from the O3 run. And the second presents constraints on cosmic strings from O3. In addition to me, I'm pleased to introduce our wonderful panel. Camille Janssens will talk about detector characterization. Katerina Martinovich will discuss parameter estimation and upper limits. And Tom Collister will talk about implications of the O3 isotropic upper limits for a background of compact binaries. From the cosmic string side, Pierre Auclair will introduce cosmic strings and describe the burst search for individual gravitational wave events from cosmic strings. And Mary Sakellariadou will discuss the stochastic search and exclusion plots combining multiple measurements. One housekeeping note is that we will have a question and answer session at the end. Please type your questions in the Q&A box that you'll see on Zoom. We'll monitor those throughout the talk, but we'll go through them at the end. Okay, so first we'll describe the isotropic paper. I've linked to the archive number of the paper here so that you can read it in more detail if you're interested. I'm just going to give a short introduction before passing it off to Camille. So the gravitational wave background is unlike some of the other webinars you may have attended recently by the LIGO collaboration, in that we're not interested in individual detectable events, but rather a superposition of many events or many different types of sources that we characterize statistically. So for example, I've given some example of sources here, and in the very center, I've got unresolved astrophysical sources. So instead of thinking of an individual binary black hole merger or binary neutron star merger in the relatively nearby universe that can be observed as an individual event, what we're interested in is the entire population of all of the binary black holes or binary neutron stars throughout the entire history of the universe, whose collective sum creates a relatively constant gravitational wave signal that's very small, but that we can try to find by integrating over large amounts of data. There's also many cosmological sources that could contribute to a gravitational wave background, and making this a very interesting probe of many interesting kinds of physics. So two examples that are on this slide are cosmological phase transitions. So bubbles can form in the early universe, and the collisions of these bubbles can produce gravitational waves, which we can detect potentially, as well as cosmic strings, which are line-like defects that can form in phase transitions, and cusps and kinks in these strings can produce gravitational wave bursts that could be detected individually, or their sum, the superposition of all of these gravitational wave events, could form a gravitational wave background. And I've listed some references for reviews where you can read more about many different types of sources at the bottom. All of these different sources are characterized by the energy density in gravitational waves, and typically we normalize it in logarithmic frequency bins and normalize it by the critical energy density needed to have a spatially flat universe. So that is shown in the upper right, and this is the fundamental quantity that we'd like to measure. So I'd also like to just briefly discuss the strategy that we use to search for a gravitational wave background, which is based on the idea of cross-correlation. So here I've got an equation defining our basic search statistic, the cross-correlation, and there's several components. In orange, I've highlighted the actual cross-correlation where we multiply the gravitational wave data H from two different detectors, and then we're going to average that over a long period of time. In blue, I've highlighted the overlap reduction function, which is a factor that accounts for the detector network geometry and the response to gravitational waves. And there's also a normalization that means that this statistic is an unbiased estimator for the energy density in gravitational waves omega, which is shown in the left box, bottom left box. We also can have an estimator for the uncertainty, which is shown in the bottom right, which allows us to create, to determine a statistical significance. So I've got a movie that just illustrates the basic principle of this search. So here in the top left panels, in the top two panels, you can see gravitational wave data being taken from two hypothetical simulated detectors in black, but there's also a common correlated, much smaller gravitational wave background signal in green. And while this green signal is very much smaller than the noise, and it's not something that we'll be able to see by eye, just looking at the data, by applying this cross correlation in the bottom two panels, you'll be able to see that the cross correlation average converges to the true value in green. And in the frequency domain, you'll also be able to see that the spectrum moves from the noise, detector noise power in red to the actual signal spectrum in green. So if I play this movie, you'll kind of see that as a function of time, as we collect more and more data, eventually we gain confidence that we're seeing a signal and we're able to detect something. And we're able to also make measurements of the energy density spectrum as a function of frequency. And different models have different characteristic spectrum. Okay, so now I'll turn it over to Camille, who will describe how we actually apply this search to real data. Please go right, Camille.
The results we present today are based on the data taken during the third observing run by LIGO Hanford, LIGO Livingston, and Virgo. And the third observing run started April 1st, 2019 and ended March 27, 2020 with a 1-month break, leaving in total to 330 days of data. So on the next slide. I also would like to mention it's the first time these 3 interferometers are used in the advanced detector era, because for previous runs only LIGO Hanford and LIGO Livingston were used in search for a gravitational wave background. Now we added Virgo. So the advantage of this additional detector in search for a gravitational wave background is it improves our high frequency sensitivity. And at the same time, it also enables us to better distinguish between different polarizations. So in each of the 3 detectors, we observe h of t, so a certain spectrum. And we combine them using cross-correlation, as Andrew mentioned earlier. And we take them in all possible pairs. So Hanford-Livingston, Livingston-Virgo, and Hanford-Virgo. Once we have these cross-correlation pairs, we combine them optimally by using the weight of the individual sensitivity of the pairs into an overall cross-correlation function, C of f. To the next slide, please. So we analyze data within the frequency range starting at 20 Hertz and going up to 1726 Hertz using time segments which are 192 seconds long. Furthermore, we coarse-grained our frequency resolution to 1/32 Hertz. As I mentioned earlier, there are 330 days of data, but during this period, not all interferometers are observing coincidentally. So for each pair of interferometers, we lose about 40% in the light blue due to non-coincident data taking. Of the remaining 60%, we lose another roughly 10% in each pair because of bad data quality time segments. And for this, we have some data quality measures in place. First of all, we have category 1 vetoes, where we reject all times where we were injecting noise ourselves in one of the interferometers and so on. But also there are these non-stationarity cuts where we reject times with too much non-stationarity in the data. For O3 data, this analysis, we have for the first time implemented gating in the gravitational wave background search, on which I will explain more on the next slide. So in both LIGO Hanford and LIGO Livingston, there was a large population of loud glitches. And when they were removed, with the non-stationarity cut, this was leading to a removal of more than 50% of the coincident lifetime. To prevent this large loss of data, we decided to gate these glitches. And gating basically zeroes out the data of these glitches, as you can see in the left figure. So in blue, we have initially the glitch, and in the orange gated data, this glitch is zeroed out. And this introduces some dead time, but it's extremely small, smaller than 1%. And as you can see in the right-hand side, it properly removes the bad features from the glitch. Furthermore, there has been some additional studies, and gating has no impact on our ability to recover a gravitational wave background. Next slide, please. Apart from the time domain data quality cuts, we also look at data quality in the frequency domain, where we notch certain frequencies with a known instrumental or environmental contribution. Notching is basically the equivalent of gating in the frequency domain, where we now zero out frequencies instead of time segments. And we do this, for instance, for calibration lines, scattered light noise, and so on. The formula on the left-hand side shows the definition of the coherence, where Si and Sj are the same data as Hi or Hj. So it's the strain of our interferometers I and J. And in the figure on the right, we see the number of times we observe a certain level of coherence in our analysis. For just purely Gaussian data, we would expect something along the black line. We notice that in orange before notching, there are several bins which are significantly different from our expectation of the black line. But after notching, we correctly remove these outliers because they are linked to known instrumental or environmental sources. Next slide, please. Apart from this time and frequency data quality, we also investigate the effect of global coherent magnetic fields and how they can mimic a gravitational wave background. To study this effect, we need two elements. First of all, we need precise measurements of magnetic fields at the sites. And this we can combine in magnetic coherence spectra, as you can see for Hanford-Livingston in the top panel. Apart from this magnetic coherence, we also need to know how these magnetic fields couple to our interferometer. And therefore, we measure on a weekly basis magnetic coupling or magnetic transfer functions, as you can see for Hanford in the bottom panel. With these two ingredients, we can construct the magnetic cross-correlation mimicking a gravitational wave background in the formula on the right, where Ti and Tj are the coupling functions of the magnetic field to the interferometer for interferometers I and J, where the real part of Mi, Mj is linked to the magnetic coherence, so the top figure on the left. If we move to the next slide, we see how this magnetic budget looks like, which is an estimate of the amount of magnetic correlated noise, and it's this large red band at the bottom of the figure. Then we have also the red curve, or the 2 sigma PI curve, or power law integrated curve, which is a figure of merit for our sensitivity to power law-like signals, so signals with a broad spectrum. The black curve on top, which is the 2 sigma gravitational wave curve, gives our sensitivity to signals in each frequency bin itself. So to compare if there is magnetic contamination, we need to compare the trend of the red magnetic budget band to the red 2 sigma PI curve. And we see the trend is well below this power law integrated curve. So we conclude there is no broadband magnetic contamination. For the narrowband magnetic contamination, we compare the upper part of the magnetic budget, so the black dashed curve, to the individual sensitivity in the frequency bins, the black curve or the black 2 sigma curve. And again, we see that the black dash curve is well below the black curve, and we conclude there are no narrowband magnetic contaminations as well. With this, I would like to conclude the data quality and hand over to Katarina.
Thank you, Camille. I will now walk you through some of the main results from the stochastic analysis performed on the data collected throughout the third observation run. And in order to do so, I'm going to actually take you back and remind you of a plot that Camille showed earlier, and that's the cross-correlation function. What's particularly exciting about this cross-correlation function is that it is the first time in the advanced detector era that we actually combine all three baselines available, meaning Hanford, Livingston, and including Advanced Virgo. Now, what we actually gather from this data is that it's a consistent with uncorrelated and Gaussian noise. In other words, we see no sign of a gravitational wave background from the data in O3. This, however, doesn't stop us from doing science and improving results compared to the O2 run. So what we do is we actually take different models and we try to fit them to O3 data and place upper limits on these models. And we do this using a hybrid frequentist Bayesian approach, where we use this frequentist constructed statistic C hat. We build a Gaussian likelihood where we try to fit some omega m model, and we then try to learn something about the parameters within that model. In particular, the models that we consider in the stochastic analysis are a power law model for gravitational wave background. We also consider a scalar vector tensor power law, meaning inclusion of additional polarizations, somehow postulated by beyond GR theories. We also consider models that include magnetic contamination that can mimic gravitational wave background, something that Camille talked about and I will briefly touch upon later, as well as models of compact binary coalescences where we take into account detailed merger rate functions, etc., which Tom will talk about later. Next slide, please. Thank you. So now I'm going to show you some of the upper limits placed on these gravitational wave backgrounds, and I'm going to start off with the power law background. This power law model contains two parameters. One is omega ref, omega reference, which is the amplitude of the power law, measured at reference frequency, which we take to be 25 Hertz throughout the analysis. And then the second parameter is alpha, the spectral index of the power law. And what we do is, for different choices of priors, place upper limits on this amplitude of the power law. And what I've shown here is only a few examples of the type of limits we place. In this instance, I've presented results for a log uniform prior on amplitude, ranging between 10 to the minus 13 to 10 to the minus 5, as well as two different alpha prior choices. The first one considers alpha fixed to 0, which considers some spectra that could potentially come from cosmic strings. And then the second one being alpha 2/3, which could resemble a spectrum coming from compact binaries. And what you can see here for both of these alpha choices, we see improvement compared to the O2 run in factors of 6 and 8.8 respectively, which is great to see. On the right-hand side, I show a corner plot for another type of search we performed. In this instance, our choice for prior and alpha is to have a Gaussian function centered around 0 with a standard deviation of 3.5, so not really have any assumptions on what the value of alpha is. And if we do that, we see that the posterior and omega ref indeed drops off, and this is exactly how we are able to place upper limits on our gravitational wave backgrounds, even though we have no detections in O3. Next slide. Now I'm going to show some of the upper limits placed on non-GR backgrounds that I mentioned earlier. This is a follow-up from a study done a few years ago that showed the power of the stochastic analysis. We were able to show that we can actually, with stochastic data, single out different types of polarization of gravitational waves, be it tensor, vector, or scalar. And in this instance, how we model omega is we take linear superposition of all the contribution from these three polarizations. And each polarization has its own pair of parameters, omega amplitude and alpha spectral index. Here, the beta parameter that you see is simply a ratio of the overlap reduction function of that polarization relative to the standard overlap reduction function that we know, which is associated with a tensor polarization. So in this instance, if we consider polarization to be tensor, beta would simply be 1, for example. And if we take this approach and consider a log uniform prior on amplitude and that marginalized prior on alpha, what we see for all polarizations, tensor, vector, and scalar, is improvement across the board, ranging from a factor of 5 to 2.9. What was particularly exciting about this part of the analysis was that we could see the power of Virgo in helping us improve these upper limits on non-GR backgrounds. Next slide, please. And finally, I'm gonna talk about a novel approach added to the analysis of the O3 data, something that is meant to be complementary to the magnetic noise budget analysis. And this is trying to find a joint fit for magnetic correlated noise and a gravitational wave background present. So this was a follow-up from a study done recently, where we considered how exactly magnetic correlated noise could mimic a gravitational wave background. And what you see here on the right-hand side on the plot is actually data taken by a magnetometer on site near Virgo during the O3 run. And what's clear to see from this plot is that this isn't any type of random Gaussian noise. In fact, there are peaks, clear coherences here that we refer to as Schumann peaks, and these need to be carefully calculated and included into analysis to make sure we don't confuse this coupling to our strain with an actual gravitational wave signal. So one way we do this is we model the background from the local magnetic field using these magnetometer measurements, and then we model the coupling to the strain channel using the transfer function that Camille also mentioned, this TI for each baseline. And each coupling function comes again with 2 parameters, kappa and beta, amplitude and spectral index. If we then try to search for a correlated magnetic noise model within the O3 data, we find that this model is not preferred over Gaussian noise with a log base factor of magnetic to noise of minus 0.03. And likewise, we see that if we try to fit correlated magnetic noise and a power law, gravitational wave background power law, we see that this type of model, again, is not preferred over Gaussian noise in the O3 run with the base factor of minus 0.3. Now, what these numbers suggest is what Camille said as well, which is that O3 run didn't have to worry about magnetic contamination. However, we know that with increased sensitivity of our detectors, this could pose an actual problem in the data analysis. So this addition to the O3 data will be particularly useful in the future. I will now turn over to Tom.
All right, great. Thank you, Katarina. All right, so having seen these results, having seen our updated limits on the stochastic gravitational wave background, we can now try and understand these limits in the context of different classes of gravitational wave signal that might contribute to the background. And so in just a couple of minutes, we're going to hear about cosmic strings from Pierre and Marie. Right now, I'm going to talk about implications of the search for the population of distant astrophysical compact binaries. And so one question that you might have is a non-detection of the gravitational wave background at this point surprising? So to try and answer this question, we can work in the other direction and try and forward model the expected gravitational wave signal given what we know about compact binaries. So if you want to predict an expected gravitational wave background or forecast a stochastic signal, you need to know 4 ingredients. You need to know how massive binary black holes are. You need to know how rapidly they spin. You need to know how many of them there are, so the local merger rate today. And then finally, you need to know how rapidly the binary black hole merger rate or the compact binary merger rate evolves with redshift. So fortunately for us, we know a little bit about compact binaries. We see some directly in the local universe. And so we can use these direct detections to actually tell us about the first 3 of these 4 ingredients. So next slide, please. Okay, so first, let's talk a little bit about what we know about compact binaries. So first, binary black holes. At this point, we've seen roughly 45 odd binary black hole systems. And so we have, at this point, a pretty good measurement of their mass distribution. We also know that they appear to exhibit low effective spins. And then finally, we also have a reasonably good estimate of their merger rate to within an accuracy of about 10 per cubic gigaparsec per year. Now, in contrast, we've only seen 2 binary neutron stars, and so we don't know as much about these systems. But what we do know is that their masses appear to range between 1 and 2.5 solar masses. And then their merger rate appears to be on the order of a couple hundred per cubic gigaparsec per year. Now, in contrast, we have seen at this point no clear neutron star black hole binaries. And so for purposes of forecasting their expected contribution to the gravitational wave background, the best we can do is to choose some fiducial mass, say 1.4 plus 10 solar masses, and then take an upper limit on their merger rate from past observing runs, say from O2. So this collectively gives us the first 3 of those 4 ingredients that we need to predict an expected stochastic gravitational wave signal. For the 4th ingredient, how the merger rate evolves with redshift, the best we can do really is to just assume something that is astrophysically plausible. And so what we do here is we will assume that the compact binary merger rate traces star formation with log uniform distribution of time delays between binary formation and their eventual merger. So next slide, please. So if you put all these ingredients together, you get the forecast that's shown on the left. So in red and green, we have our predictions for the stochastic background with uncertainties due to binary neutron stars and binary black holes. The dashed black line, in turn, shows our upper limit on the possible contribution from neutron star black hole binaries, given that we haven't actually detected any of this class of source. Now, if you put the binary neutron star and the binary black hole bands together, the total contribution, the total expected contribution from these systems is shown in the shaded blue band on the right. Now, towards the top of the right-hand figure, there's a solid black line. And this is the same power law integrated curve that Camille discussed earlier. This is essentially denoting the sensitivity of our present day searches. The fact that there is a good order of magnitude between this black curve and our blue forecast means that it's not surprising at this point that we haven't detected a stochastic signal. However, the dark gray dotted and dashed dotted lines, the dark gray dashed and dashed lines below the black curve show the projected sensitivities for future detector configurations. And so what these curves tell you is that as we move towards the so-called design and A+ configurations, we really do expect to be probing the energy regimes where we plausibly expect the stochastic background to sit. Next slide, please. Okay, so in the previous few slides, we talked about how that 4th ingredient that we needed to predict a stochastic signal, the evolution of the merger rate with redshift, wasn't something that we knew. We had to assume it. For the case of binary black holes, at least, we can try and not even assume it, but just go out and measure what it actually is. So in general, if we believe that binary black holes are tied to a stellar origin, their merger rate as a function of redshift probably looks something like this blue curve here, with an initial rise as we look out towards higher redshift, a peak, and then an eventual decline, simply because in the very early universe, there aren't enough stars to be forming very many binary black holes. Now, in principle, we could try and measure the shape of this curve. The problem is that most of the features in this curve, like the peak and the decline, happen at redshifts or distances that are just simply beyond the range of our present day detectors to see, which I sort of denoted with this dotted vertical line. However, we can try and get around this limitation by combining what we know both from the stochastic background and what we know about direct detections in the local universe. In particular, direct detections of nearby binary black holes tell us what the merger rate is down at z=0. And it also tells us a bit about the initial slope of the merger rate with redshift. In turn, even though we haven't detected a stochastic signal, because the stochastic background is formed essentially from all binaries in the universe, an upper limit on the gravitational wave background gives us an upper limit on the total area that can exist under this curve, which is sort of shown in this like shaded light blue band. By combining these two sources of information, we can try and constrain the global character of this merger rate function. Next slide, please. So we've done this for O3. If you put these two sources of information together, this plot shows the resulting constraints we get on the binary black hole merger rate as a function of redshift. Each blue trace, each light blue trace shows one possible curve that is consistent with our data. And then the solid gray bands show our central 90% credible bounds on the merger rate. Now in O2, the non-detection of a gravitational wave background was extremely constraining in this kind of analysis. And interestingly, in O3, our stochastic non-detection has become much less constraining. And so to try and illustrate why this is the case, I've annotated this plot with a horizontal black line. And this is a cartoon, so this particular line shouldn't be taken too literally, but in essence, the non-detection of a gravitational wave background imposes this barrier above which we don't believe the blue curves should lie. Now, in moving from O2 to O3, we've improved our sensitivity, and so this barrier has marched downwards to become more stringent. At the same time, the constraint on the low redshift slope of the merger rate has improved and tells us that that slope is shallower. By virtue of being shallower, all of these curves already miss essentially the barrier posed by a stochastic non-detection. So this explains the change in the relative amount of information here. That said, as we continue to integrate over more time with increased detector sensitivity, this barrier due to a non-detection will continue to march downwards, and we expect that by design sensitivity, it will again become very constraining. So thank you. I think I'm now going to turn it over to Pierre.
Thank you, Tom. So let me move on to the second article of this presentation, namely using data from the third observing run to constrain cosmic strings. So to the next slide, please. So cosmic strings are one-dimensional objects that may have formed in the early universe after a phase transition. Grand unification theories are candidate for such phase transition, so detecting cosmic strings would be a smoking gun to constrain grand unification theories or any beyond the standard model theory that predicts phase transition in the early universe. The network of cosmic string, as you may see in the numerical simulation on the right-hand side, is composed of infinite string in dark, as well as closed strings, loops, that you see in blue. In the present analysis, we focus on the gravitational wave signatures of cosmic string loops in terms of both bursts that are individual signals that we may detect in our detector, and as well as a contribution to the stochastic background of gravitational wave, as Mary will show later. This network of cosmic string has a very nice property, which is called scaling, that tells you that all the characteristic length of the network evolve self-similarly with the Hubble radius. And this property means that the network of cosmic strings survives for a very long time, and so that cosmic string loops can emit gravitational wave from their formation and throughout the history of the universe. So they are a source that is omnipresent in the universe, and this is a reason why they may have a stronger signal in our frequency band. To the next slide, please. So cosmic string loops may emit gravitational wave in different ways. Two of them are presented on this slide. So on the left-hand side, you see kinks. So kinks are discontinuities in the tangent vector of the string. They propagate along the string at the speed of light. and they emit gravitational wave in a certain beam, and the direction of the beam moves as the kink propagates along the string. So you should see this kink as a lighthouse emitting gravitational waves, and you see the burst of gravitational wave when this beam is directed directly towards the Earth. On the contrary, you have also cusps on these strings, and you should see these more like the sound that you hear from a whip. So the tip of the cusp goes instantly at velocities very close to the speed of light and emit gravitational wave in a very a certain beam. And then after this emission, the cusp dissipates and will then reappear after one oscillation of the loop. There is also a third possible source of gravitational waves, which is the collision of two kinks. And this source was not used in previous LIGO-Virgo analysis because this source is very weak with respect to cusp and kinks. However, it turns out that the number of kinks for loop oscillation is a number that is still unknown. And in the present analysis, we've decided to promote this number of kinks to be a free parameter. Hence, when the number of kinks is very high, the number of kink collision goes quadratically with the number of kinks. So when the number of kinks is high, the contribution from kink collision can become dominant. And this is the reason why we've included that in the O3 analysis. The waveform for all these burst events has been known for 2 decades and is shown on the formula on the bottom left side. So the strain goes like the power law with respect to the frequency, whose exponent is characteristic of the type of bursts. So 4/3 for cusps and so on for kinks and kink collisions. And the amplitude is also known, depends on the length of the loop, as well as its redshift, and also on a crucial parameter, which is the string tension. So you should see the string tension really as the energy scale of the string. And knowing the string tension, we could potentially go back to the energy scale of the phase transition that produced the string. And this would tell us a lot about beyond the standard model physics and tell us at which energy scale the transition occurred. Now to the next slide, please. So here you see the results from the analysis for individual bursts in the data. So let me first focus on the right panel, which shows basically the background distribution of bursts in our search. So it turns out that there are lots of artificial glitches in the data that may trigger our match filtering algorithm. And this artificial trigger may happen at 2 different detectors at the same time with a probability which is non-zero. And that has been estimated by doing artificial time shifts between the data from different detectors and looking at coincident events. So we know by time shifting that these events are artificial, and hence we can deduce the shape of the background. And in the real data, all the candidates that we've found are consistent with the background at 1 sigma. So we do not claim any detection of cosmic string events, we can only use this non-detection result to put upper limits on the parameters that we're interested in. On the left-hand side, there's also another result from our burst analysis, which is the burst detection efficiency. So we have a selection effect because our detector cannot detect all the individual bursts that could happen in the universe. It only detects those with a very high amplitude. So we've calculated by injecting fake signals in the data and running our match filtering algorithm on those, the probability to recover signals with a given amplitude. And this is given by the curve on the left panel, which of course for very high amplitude goes to probability 1, and then transition to very low amplitude to probability 0. And we need this curve to put upper limits on the parameters we're interested in. So now to the next slide, please. So to go beyond and put upper limits on the string tension and the number of kinks, we have to assume something about the population of cosmic string loops in the universe and throughout its history. So to that end, we have to assume certain models that are, and we use some that are present in the literature. So we used 2 models that are calibrated with numerical simulations, model A and model B. So model A comes from publications by Blanco Pilado and collaborators, and model B from publication by Larissa Lorenz and collaborators. The main difference between those two is the fact that model B predicts an extra population of small loops at very small scales, and this induces an additional contribution at high frequencies, precisely in the frequency band of LIGO Virgo. And this is one of the reasons why the constraints for model A and B are different. In this analysis, we've decided to add another set of models that we've labeled model C, that extend both model A and B and try to interpolate between those two to gain understanding on exactly what the differences and what the burst search and the stochastic search, to what both those search are sensitive to. So assuming something for the population of cosmic string loops, we can calculate the expected rate of burst in our detector by integrating and taking into account our detection efficiency, the epsilon A function at the bottom left. So meaning that we select only events with very high amplitude. And we assume also these bursts to follow a Poissonian statistics, which is well known and given by the formula on the upper right side. We have a mean that is characterized by the expected rate of bursts multiplied by the observation time. And it's given this Poissonian law, we can estimate the probability of non-detection, and we exclude parameters that are non-consistent with the non-detection of bursts. And this translates into this small formula at the bottom in a relationship between the expected rate of burst and the observation time. So for the future, we have two ways to act on this formula. First, we can increase the sensitivity and hence increase the expected rate of bursts on the left-hand side. And we can also run the detector for longer and decrease the right-hand side. Okay, so now I let Mary continue and present the stochastic results.
Okay, thank you. So I will move with the stochastic search for cosmic strings. So the incoherent superposition of bursts from loops through the entire history of the universe is going to produce a stochastic gravitational wave background. As you have seen a bit earlier from the presentation by Andrew, the energy density of gravitational waves in a logarithmic interval of frequency f and normalized at the critical energy density is this dimensionless parameter omega GW as a function of frequency that you will see here. So the spectrum of the stochastic gravitational wave background produced from string loops as a function of the frequency is given by the second expression where h naught is the Hubble parameter. We integrate over all the redshift and over all lengths of loops, and we're going to add the contribution to the strain coming from kinks, cusps, and king-king collisions that Pierre said before. After we have calculated what will be the burst rate per redshift and per loop size for every given model of loop distribution function. Can we go to the next slide, please? So I think that you missed one slide. Exactly. So here you see in these panels the prediction for the gravitational wave energy density spectra for the different models that we said before for our loop distribution, and where we vary the number of kinks per loop oscillation. In these panels, we have fixed the string tension G mu to be 10 to the minus 8. So what you see in every of these panels is the energy spectra of three different components: cusps, kink, and king-king collisions. Cusps is in red, kinks in green, and king-king collisions in blue, as well as the 2 sigma power law integrated curves for the all three isotropic stochastic search, and also projection for the Hanford, Livingston, and Virgo network at design sensitivity and for A+ detectors. In the top panels, you see what is the contribution if the number of kinks is 100. And clearly from there, you see that if you have many kinks, then the contribution from the king-king collision is bigger. You see that is bigger, the blue curve, okay? In the bottom panels, we have what we call the one variant of this model C. In one side, on the left, you have for one kink, and on the right, you have 100 kinks. So you will see exactly that if we have one kink, then from the waveform that before Pierre showed you, it's clear that the major contribution will come from cusps. So you see at the top, the pink curve, whereas if the number of kinks is high, then you have the kinking collision. So you go to the right-hand side and you have the blue curve. Now, as Pierre said before, something which is particular for the models B and C, you have an extra population of small loops. And this gives clearly different kind of predictions and therefore different conclusion kind at the end that we will have the predictions for the string tension. Now, something that I would like to draw your attention is this bottom panel, which I put in a frame, which is this model C. So this model, the way that we have fixed the parameter, it mimics the loop production function of model A in the radiation-dominated era and model B in the matter-dominated era. Now, this extra population of small loops of the radiation-dominated era can be neglected, but not of the matter-dominated era. And this leads to this characteristic peak, which you see in this omega GW plot. This is something important because this is going to lead to some particular features that we will see in the exclusion plot that I will show you in a minute. Can we go to the next slide, please? Okay, so we're going to do this stochastic search. So how are we going to do that? We're going to do a Bayesian analysis, taking into account the precise shape of the background given for any choice of our model, this M for model 1, model A, model B, and the two model C. For as a function of the frequency, where our free parameters will be the tension and the number of kinks. And we play with the number of kinks from one extreme, up to 200. Not above that, because there are numerical simulations which pose this kind of constraint. And then the first thing we have to do, we have to calculate the log likelihood function, assuming a Gaussian distribution noise. And this is this big expression which you see here, where this C hat is the cross-correlation estimator for the pair of your detectors ij at a given frequency f. And we have three pairs, Hanford-Livingston, Hanford-Virgo, and Livingston-Virgo. Okay? And then the sigma square is the variance of your estimator at the frequency f. So at the end, what we are going to do, we're going to calculate the 95% credible interval for our tension after we have fixed the number of kinks. And to do so, we're going to use the Bayes theorem with priors for the tension between 10 to the minus 18 and 10 to the minus 6. Why that? Because 10 minus 6, which corresponds to GAD scale strings, kinks that they have been put at the GAD scale, it's excluded from the CMB data. We went down to the 10 to the minus 18. Well, that's a good guess. You could go even lower. And if you do so, we have checked that our results are robust. And the prior for the number of kinks is the delta function for each value of nk. Next slide, please. So here I'm showing you the results. These are the exclusion plots. So for the stochastic search, we put constraints from combined O1, O2, O3 data, and for the best search, constraints from the non-detection results of O3. Look at the top panel on the left, model A. Actually, the derived power spectrum there is much weaker than the other cases. So for sure, that means that we have weaker constraints. Actually, the constraint that you get from the best is so weak that doesn't show you the picture. So the constraint we have for the string tension for model A, taking into account our O1, O2, O3 data, is that the string tension could not be bigger than 9.6, 10 to the minus 9 to 10 to the minus 6. Let me go to the model B. Now, here actually, what you can see, if you are in the second column, the model B and the model C2, which is one variant of the model C, this agnostic model, let's call it, they have some similarity. Why do they have the similarity? The reason is the following. The C2 model has been chosen so that it mimics the loop production function of model A in the matter-dominated era and of model B in the radiation-dominated era. However, in the LIGO Virgo band we're interested, the stochastic background is dominated by contribution of loops in the radiation-dominated era. So it's clearly why you have the model B and the C2 to give similar results. Let us move to the model C1, bottom left. Remember what I said a couple of minutes ago. You have this peak in the omega GW for this model, and this is actually the reason for these features that we see here. As a matter of fact, I put it with an arrow, there is one case where the best analysis gives the tighter results, and this is for the model C1 if you have that the number of kings is greater than 7. So here you can see the constraints we have. Did we do better than the previous analysis? We did better. In the previous analysis, remember, we had only model A and B and only one king. Now, if you take our results and you translate them back to models A and B with one king, we gain 1 or 2 orders of magnitude for model A and B. So here we have more kings as well as a free parameter and these new variants of model C, the C1 and C2. How do we do with respect to other experiments? Pulsar timing array, CMB, Big Bang nucleosynthesis. Here it is. For the model A, PTA does better than us. It puts a stronger constraint 10 to the minus 2. However, for model B and model C1, we have the strongest constraints. For model C2, CMB does as good as us. And there is one case for model B, for the parameter of mu q, LK, such that we put a constraint that tension cannot be bigger than 4 times 10 to the minus 15, and this is the strongest constraint which exists so far in the literature. Now, so far, I took the number of cusps equal to 1. Well, that's another free parameter that simulators have not told us yet. However, the number of cusps per period of string oscillation scales with the number of harmonics on the loop. So it could be a free parameter, it could be much bigger than 1. That was not studied before by anyone. What would be the effect of playing with the number of cusps? So we did this exercise, and what we found is that for model A, we have a slightly weaker bound, but for models B and C, our results are robust. They are insensitive in what is the value of the n cusps. So what about the future? Well, in the future, certainly with a better kind of sensitivity, we're sure that we're going to put even stronger results. It is extremely good because, as it has been said before by my colleagues, this is a way to put constraints to physics beyond the standard model, reaching a regime which cannot be reached by, for instance, LHC. And I will pass that to Andrew.
Great, thank you, Mary, and to everyone on the panel. I'm just going to close with some concluding thoughts. So first, all of the data for the papers that we presented today are available publicly so that they can, every results can be reproduced. The O3 isotropic results can be used to constrain any model of an isotropic gravitational wave background using the formalism described by Katerina earlier. And also the PI curves that were shown are available so that one can compare a model to the sensitivity curves. So I've linked to that on this slide. And the results from the cosmic strings paper are also available online at this link. Another direction that we didn't discuss in this presentation is to place constraints on anisotropies in the gravitational wave background. This is a plot from the analysis of the O2 data, the former observing run, showing constraints on the gravitational wave background power in different sky directions. And then finally, I wanted to close with a note of optimism. This plot shows many different examples of models, some of which we've discussed and some of which we haven't, that could all potentially be probed by current or future experiments searching for the gravitational wave background. And you can see that there's really a huge range of observations from the CMB to pulsar timing arrays to LISA in the future and to ground-based interferometers that will, in the coming years, probe many of these models across a huge range of frequencies and potentially learn very interesting and important information about astrophysics and cosmology. So it's a very exciting time to be studying the gravitational wave background. Okay, with that, I'd like to thank everyone for attending, and now we will take some questions. So I'm going to look at these questions in the order that I see them on my screen, and then either answer or pass them off to panelists. So the first question is from Mandeep. So the way the analysis is done assumes that no detection of the background gravitational wave that is incoming can be determined, does this assume that the wave hits all 3 detectors within a small time window, and then this constrains the frequency range that is searched for? So in fact, the assumption for an isotropic background that we're implicitly assuming that there's a constant or roughly constant signal coming from all sky directions simultaneously. So in fact, the correlated signal shouldn't vary in time because of the detector responses. What really limits the frequency range is more the sensitivity of the detectors as well as the geometry of the detector network. There are ideas to look for isotropic backgrounds where the time dependence, where it's not stationary, but you could have the binary black holes, for example, kind of are more popcorn-like than continuous. And so there's some ideas to have a different search that would be optimized for that kind of signal. And an anisotropic background, which, as I mentioned, we also study, that does take into account the fact that the rotation of the Earth will cause the signal the amplitude of the signal to change in time as for example, if the galactic center moves through the detector network's sensitive spots and less sensitive spots. So yeah, that's a great question. Okay, there's another question. Second question is Ziapor is asking that the C of F curve is far from being white noise. So let me go back to the C of F curve. Although it's not a power law, there are many features. How can you be sure that they're really noise, instrumental, etc.? Yeah, that's another good question. So first of all, we don't expect that the signal would appear to be white noise because there's a combination of different effects. There's the instrumental sensitivity. So if you look at this, there's an expression that I wrote down that estimated the sensitivity that depend where for white noise, this would effectively be frequency independent, but there's frequency dependence that comes from the detector power spectra, as well as this factor encoding the detector response functions. So we don't expect white noise, but this sigma also allows us to make statements about statistical significance. And the data, we've checked in several ways that the data that we observe is consistent with the null hypothesis that the data are being generated by a Gaussian process that is not correlated between detectors. Okay, next question. So there's what's the final bound on omega GW below the expected sensitivity? The O3 sensitivity around 25 Hertz seems quite a bit larger than the quoted bound. Thanks for the explanation. So yeah, this is related to the prior that we use a log uniform prior to place upper limits. Maybe Tom, do you want to say more about this question?
Sure, I can just chime in. So indeed, this is all about priors. So these sensitivity curves that we were showing, the PI curves. The idea is if you you have your favorite model for a stochastic gravitational wave background, it has some slope. And if you want to know how loud or the amplitude of that signal with a given slope that would be required to be detectable, you can take your power law curve or your prediction and slide it up until it's tangent to, say, that black solid line. And at the point where it's tangent to the line, that's when it is, I think in this case, like it would be expected to have a 2 sigma signal to noise ratio. This metric of this detection metric, or sort of this idea, though, implicitly assumes a prior belief that it's equally likely for the stochastic background to just have any amplitude. And like Andrew said, when actually doing this analysis, we take a slightly different prior belief that it's equally likely for the amplitude of the stochastic signal to live in any logarithmic amplitude. So in other words, to be in any decade of amplitude. these are different choices. Both of them are like, defensible, and there may be some good reasons to choose one over the other. But the practical effect is that the log uniform prior generally shifts your upper limits down to smaller values by just a little bit. So that's the reason for the difference that you very astutely noted.
Great. Yeah, so I just want to note that we're at the hour. So I know that there's a lot of demands on people's times, and these days there's many telecons to attend. So we will continue. I think we can continue answering the questions that are currently in the chat. So we'll answer those. But for those who have attended, for the full hour, thanks for attending. And we understand if you have other obligations. Okay, so there was also a question. I see Tom was typing an answer, but maybe we can just answer it live. So they were surprised by the fact that there were 2 BNS events. I thought only one was confirmed conclusively. Tom, do you want to answer?
Yeah, so I started typing and then it got very long. And so I figured it would just be better to answer this live. So the 2 events that we're talking about here are 1708-17 and 1904-25. 17.
Tom, I can't actually hear you currently.
Oh, we cannot hear you, Tom.
Okay, I think, yeah, I think maybe the basic, maybe Tom will type more details later, but I think maybe the basic idea is that I think based on masses.
I think I'm back now.
Okay, yep, go ahead, Tom.
All right, this is the peril of having AirPods around the apartment, is sometimes one's computer decides to randomly divert sound. Okay, so yeah, so like I was saying, 1708-17 was accompanied not only by a gravitational wave signal, but by an electromagnetic signal. And so that pretty unambiguously told us that matter was present, and hence it couldn't be a binary black hole. It had to be a binary neutron star. Now, in contrast, 1904-25 neither had an electromagnetic counterpart, nor did the gravitational wave signal have any evidence for matter effects like tidal deformation. And so, strictly speaking, you're absolutely right that we cannot unambiguously say this is a binary neutron star with matter rather than 2 binary black holes. However, just with the sort of keeping in mind that our motivation here is just to forecast something that's astrophysically plausible, the masses for 1904-25 are much more consistent with what we know about binary neutron stars than anything we've seen, in the population of emerging binary black holes. And so again, with this vein of constructing something astrophysically plausible, it makes sense to drop it in the binary neutron star category. Another attitude that one can take is that the labels BNS and BBH are more sort of phenomenological labels, where the binary neutron star label is applied to things with masses, clearly below 3 solar masses, and the binary black hole label is applied to things clearly above 3 solar masses. And there's no evidence at this point for anything that lives in between. And so the energy densities don't strongly depend on tidal effects. So the contributions to the gravitational wave background here would be more or less the same, depending on which category we put it in.
Okay, great. And then I see the next question is about slide 23. So I think, Tom, this will go to you again. So does the prediction here contain the peak already?
Yes, so all of these little light traces, again, that are represent our posterior probability distribution on the merger rate, are generated by this model that allows for a rise, a peak, and a turnover. And so if you look closely at any of the little blue traces, you'll see that some of them do show peaks and declines. So these are our constraints on the merger rate of binary black holes, yeah, under this sort of more complicated model. I hope that answers the question.
Okay, and then so the next question is a detector, and I think we'll take, there's 3 more questions. We'll take those, and then I think we can wrap up. So the detector noise is typically modeled as stationary. Is this assumption expected to detect potential detections of a gravitational wave background? Should noise non-stationarity be taken into account? So this was a point that Camille made on his slides. That Camille, do you want to briefly address that?
Yes. So let me see. What we basically do is these non-stationarities, one of them are, for instance, those glitches. And what they actually do is they bias our measurements, while we know these glitches are, for instance, from environmental sources and so on. So we really do not want to take them into account because they are rather polluting our data. And we want to observe this very weak gravitational wave background signal, and we do not like to have this contamination of these non-stationarities, and therefore we are taking them out either with the non-stationarity cut or using this gating method. I hope that answered your question.
Yep, thanks, Camille. And I'll just add, we also regularly do we check for the non-stationarity of the data, and we remove times that are determined to be not non-stationary enough that it would affect our analysis. So that's something we have to be very careful about. Okay, 2 more questions. Are the future sensitivity lines only for ground-based detectors? So the curves that are available on the public page, yes, these are only the ground-based detectors. There's a formalism to derive these kind of PI curves in a paper by Thrain and Romano that can be relatively easily applied to any model for a noise power spectrum. But from the 01 paper, there are still reasonably up-to-date projections for Lisa sensitivity and the low LCMB constraints that you can find on the web. Okay, and then the last question, are you able to modify the gauge wavelength observation beyond the redshift to verify distances beyond the current observation? So I'm not sure I fully understand the question, but the basic idea of the gravitational wave measurements is that background measurements is that we'd be probing sources kind of, well, for example, for the cosmic strings, Marie had a nice expression where we're summing over all the sources across distances. So we don't know the distance of any one source, but we have sources at many distances that all contribute to the background. Okay, and then I do see one last one, which is how to distinguish gravitational wave background from compact binaries and cosmic origins from the data, which is a very, very good question. And probably at first, we won't be able to do that after making a detection. Really, the spectral index contains information about what type of source. And it may take, probably at first we'll have a detection before we have a very strong measurement of the spectral index parameter that could distinguish between different models. But essentially by having more, having more data and building up SNR and using the frequency spectra is how you could distinguish different models. Okay, so thank you. So I think that's all the questions. So I just wanted to thank everyone again from the panel for giving a great presentation, and thanks to the audience members for attending and for the very interesting discussion. So I think we'll wrap it up here.